Okay, so we're looking at problem 3 from exam 3. And so in this problem, we're given this triangular block. And we're asked to find the mass of this block given that its density is varying with height, where y is the height from the top of the block, so moving up and down this side. So the first thing we're asked to do is set up a Riemann sum with n subintervals and use this to estimate what is the mass. So the first thing we need to notice is that since density is not constant, we chop the block into small pieces. So in this case, the pieces are going to be rectangles. So they're going to end up looking something like this. Okay, that's a pretty badly drawn rectangular prism, but I hope you get the idea. Here we have a height of delta y. We have this side will be 10. But this side actually is unknown to us. It's something x. So the reason for this is what we're getting these rectangles by taking horizontal slices of this object, because within a horizontal slice, the density is not really changed, since the density only depends on y, the vertical height. So that means that since this side is slanting inward, this side of the rectangle is getting smaller and smaller as we move further and further down. So we're going to have to figure out what is the value of x. So in order to do this, we can look at a cross-section of this thing. And so this entire height is 6, but if we move the distance y down from the top, then this distance here is going to be 6 minus y. And so if this distance is x and this is 12, then we can use properties of similar triangles to say that 6 minus y is related to 6 in the same way that x is related to 12. And if we solve for x, we'll get that x is equal to 12 minus 2y. So that means that the volume of the piece at height yk is going to be vk approximately equal to, let's see, so it's going to be 10 times x, which we found to be 12 minus 2y, times delta y. And so I say approximately because of the shape, it's not quite a perfect rectangle. There's a little bit of a slant on one side, but if delta y is really small, then we can basically just ignore that, and this is essentially what the volume of the piece is. In the limit, as the number of pieces goes to infinity, this is fine. So that means we can now find the mass of piece k. So that's going to be mk is approximately equal to 10 times 12 minus 2y times the density on that slice, which is going to be y over 6, and I've been forgetting this should be yk since we're at height yk. And then we still have to multiply by our delta y. So now our Riemann sum to estimate the total mass of the object is going to be the sum from 0 up to n minus 1, since we're using a left-hand sum, of, let's see, we can factor a 2 out of of this thing to get 20 times 6 minus y k times yk over 6 delta y. And if we're going to throw in delta y's and yk's, we should specify what they are. So delta y is equal to 6 divided by n, and yk is equal to 6k divided by n. So this is just from the standard definition of delta y and yk for your Riemann sums. So this would be our Riemann sum to estimate the total mass. Now in part B, we're asked to convert this into an integral. So what happens when we let n tend to infinity and the pieces get smaller and smaller and smaller? So we get the integral going from 0 to 6, because that was the bounds for y. And we'll have the 20 can come out front. We're integrating 6 minus y times y over 6. The delta, and the delta y becomes the dy. And so then for part C, we're asked to actually evaluate this integral. So let's do that. So if we use, let's multiply out first. We'll have 20 integral 0 to 6 of y minus y squared over 6 dy. Now if we use the fundamental theorem of calculus, we take the antiderivative of this thing, and we'll get that it's 20 times 1/2 y squared minus y cubed over 18 evaluated from 0 up to 6. And if you do a little bit of arithmetic, you end up getting that this is 20 times 18 minus 12. And this works out to be 120 kilograms. So that is the solution to this problem.